Welcome back, and in this video I want to talk about SSL and TLS. At a very high level they do the same thing. SSL stands for Secure Sockets Layer, whereas TLS is Transport Layer Security. TLS is just a newer and more secure version of SSL. Now we've got a lot to cover, so let's jump in and get started. TLS and historically SSL provide privacy and data integrity between client and server. If you browse to this site, to Netflix, to your bank, and to almost any responsible internet business, TLS will be used for the communications between the client and the server. TLS performs a few main functions, and while these are separate, they're usually performed together and referred to as TLS or SSL. First, TLS ensures privacy, and it does this by ensuring communications made between a client and server are encrypted so that only the client and server have access to the unencrypted information. When using TLS, the process starts with an asymmetric encryption architecture. If you've watched my Encryption 101 video, you'll know that this means that a server can make its public key available to any clients so that clients can encrypt data that only that server can decrypt. Asymmetric encryption allows for this trustless encryption where you don't need to arrange for the transfer of keys over a different secure medium. As soon as possible, though, you should aim to move from asymmetric toward symmetric encryption, and use symmetric encryption for any ongoing encryption requirements because computationally it's far easier to perform symmetric encryption. So part of the negotiation process which TLS performs is moving from asymmetric to symmetric encryption. Another function that TLS provides is identity verification. This is generally used so that the server that you think you're connecting to, for example Netflix.com, is in fact Netflix.com. TLS is actually capable of performing full two-way verification, but generally for the vast majority of situations it's the client which is verifying the server, and this is done using public key cryptography, which I'll talk more about soon. Finally, TLS ensures a reliable connection. It protects against the alteration of data in transit. If data is altered, then the protocol can detect this alteration. Now, in order to understand TLS a little better, let's have a look at the architecture visually. When a client initiates communications with a server and TLS is used, there are three main phases to initiate secure communication. First, cipher suites are agreed, authentication happens, and then keys are exchanged. These three phases start from the point that a TCP connection is active between the client and the server, so this is layer 4, and at the end of the three phases there's an encryption communication channel between a client and a server. Now, I find it really useful to explain each of these phases individually because each stage is responsible for one very specific set of functions. The first stage focuses on cipher suites. Now, a cipher suite is a set of protocols used by TLS. This includes a key exchange algorithm, a bulk encryption algorithm, and a message authentication code algorithm, or MAC. Now, there are different algorithms and versions of algorithms for each of these, and specific versions and types grouped together are known as a cipher suite. So to communicate, the client and server have to agree a cipher suite to use. Now let's step through this visually. We have a client and a server, and at this starting point we already have a TCP connection, so TCP segments between the client and the server. The first step is that the client does a client hello, and this contains the SSL or TLS version, a list of cipher suites that the client supports, and other things like a session ID and extensions. Hopefully at this point the server supports one of the cipher suites that the client also supports. If not, then the connection fails. If it does, then it picks a specific one and it returns this as part of the server hello. Now, included in this server hello is also the server certificate, which includes the server's public key. Now, this public key can be used to encrypt data which the client can send to the server, which only the server can decrypt using its private key. But keep in mind that this is asymmetric encryption, and it's really computationally heavy, and we want to move away from this as soon as possible. Now, at some point in the past, the server has generated a private and public key pair, and it's the public part of this which is sent back to the client. But, and this is important, part of TLS is ID validation. If the client just took for granted that the server it's communicating with is valid, then you could exploit this. I could create a server which pretends to be Netflix.com without being Netflix.com, and this is suboptimal. So it's important to understand, and I'll talk more about this in a second, that part of the functionality provided by TLS is to verify that the server that you're communicating with is the server that it claims to be. The next step of the TLS process is authentication. The client needs to be able to validate that the server certificate the server provides is valid, that its public key is valid, and as such that the server itself is valid. To illustrate how this works, let's rewind a little from a time perspective. So the server has a certificate. Now, the certificate you can think of as a document, a piece of data which contains its public key, its DNS name, and other pieces of organizational information. Now, there's another entity involved here known as a Public Certificate Authority, or CA. Now, there are a few of these run by independent companies, and your operating system and browser trust many of these authorities, and which ones is controlled by the operating system and browser vendors. Now, at some point in the past, our server, and let's say this is for catagram.io, created a public and private key pair, and in addition, it generated a certificate signing request, or CSR. It provided this CSR to one of the public certificate authorities, and in return, this CA delivered back a signed certificate. The CA signed a certificate, which means that you can verify that the CA signed that certificate. If your operating system or browser trusts the certificate authority, then it means your operating system or browser can verify that the CA that it trusts signed that cert. This means that your OS or browser trusts the certificate. And now the catagram.io server that we're using as an example has this certificate, and that certificate has been provided to the client as part of the server hello in stage 1 of the TLS negotiation. In stage 2, so authentication, our client, which has the server certificate, validates that the public certificate authority signed that certificate. It makes sure that it was signed by that specific CA, it makes sure that the certificate hasn't expired, it verifies that the certificate hasn't been revoked, and it verifies that the DNS name that the browser is using, in this case catagram.io, matches the name or the names on the certificate. This proves that the server ID is valid, and it does this using this third-party CA. Next, the client attempts to encrypt some random data and send it to the server using the public key within the certificate, and this makes sure that the server has the corresponding private key. This is the final stage of authentication. If we're at this point and everything is good, the client trusts the server, its ID has been validated, and the client knows that the server can decrypt data which it's being sent. It's at this point that we move on to the final phase, which is the key exchange phase. This phase is where we move from asymmetric encryption to symmetric encryption. This means it's much easier computationally to encrypt and decrypt data at high speeds. We start this phase with a valid public key on the client and a matching private key on the server. The client generates what's known as a pre-master key, and it encrypts this using the server's public key and sends it through to the server. The server decrypts this with its private key, and so now both sides have the exact same pre-master key. Now, based on the cipher suite that's being used, both sides now follow the same process to convert this pre-master key into what's known as a master secret. And because the same process is followed on the same pre-master key, both sides then have the same master secret. The master secret is used over the lifetime of the connection to create many session keys, and it's these keys which are used to encrypt and decrypt data. So at this point, both sides confirm the process, and from this point onwards, the connection between the client and server is encrypted using different session keys over time. So this is the process that's followed when using TLS. Essentially, we've verified the identity of the server that we're communicating with, we've negotiated an encryption method to use, we've exchanged asymmetric for symmetric encryption keys, and we've initiated this secure communications channel. And this process happens each and every time that you communicate with a server using HTTPS. And SSL and TLS are both architectures that you need to be familiar with if you're designing any infrastructure for AWS or implementing any infrastructure within AWS. You need to ensure that your communications are encrypted between clients and servers, and so you need to have an appreciation for how this process works end to end. Now that's everything I wanted to cover within this video, so go ahead and complete the video, and when you're ready, I'll look forward to you joining me in the next.